Yeah. Okay. Here we're trying to figure out the average speed from 2 seconds where we had only fallen 64 feet after 2 seconds, and then after 4 seconds we had fallen a total of 256 feet. And a number of you are using the concept that distance equals rate times time. So our speed should equal distance divided by time, right? And so what did you do as the calculation?
256 minus 64 over 4 minus 2.
Okay, and you ended up with
96.
96 feet per second.
Square.
Not square, that would be an acceleration. This is just velocity. Or it's just a speed, okay? Now, think about this in terms of a function. Okay, what did we actually find? Slope. Okay, stay with me here. We just found the slope of this segment FM. Okay? That is going to give us, listen, that's going to give us an average speed. And the cool thing about this, guys, is even if our model looked something like this, even if our model went from here and it went up and down and like this, okay? If we wanted the average speed between this time and whatever this time was, okay, all we would have to do is find the slope of that segment. And that would give us average speed, okay? And in fact, you might even see stuff like that on the IB exam where they ask you for the difference between the average speed. And then the point of this is that really what we're interested in is 2 seconds after we drop this thing, how fast is it going? How fast is it going? Because the longer you fall, the faster you are going to fall, okay? The longer you're in the air, the faster you're going to end up going. That's why it hurts more when you fall from higher up. Okay? It's not the distance, it's the fact that you hit the ground going at a higher rate of speed. Okay? So, yeah. So now, what we want to do here is we want to focus in on this 2-second mark. Because, obviously, at 2 seconds, it hasn't been in the air quite as long as when it has fallen for 4 seconds, so it's not going as fast. And this average speed is the average over this entire time period. But if we want the instantaneous speed at 2 seconds, okay, then we need to do a little bit better, okay? In fact, we know already that 96 is actually too high. Because in this interval, the slowest we were going was at 2 seconds. All right? So, what we're going to do is we're going to take our function, that d equals 16t squared, the distance fallen, and the next thing I want you and your partner to do is we're going to find some points first of all, and then we're going to I want you and your partner to find the slopes, okay? So, with your function, d equals 16t squared, okay? Let's get some folks on the calculator here. For 3.5 seconds, how far have we fallen? 16. What?
Sorry. 3.5 squared times 16 would be 196.
196? And we can round to the whole number. We're not doing anything real crazy here, so.
3 squared
All right.
times 16, 144.
144. 2.5 squared. Feel free to, some of you work on
100.
various ones. 2.5 squared times 16 is 100.
Yeah.
Okay.
Then 92.16.
DFT is the function.
And 2.3.
64.
Okay. 2.2.
Distance.
77.44.
And finally 2.1.
70.56.
No, position. It's like f of x.
Okay, now I want you to use this point here, but notice what we're doing with the chord that we're working with. Let me get a thin line here. What we're doing is when we go to 3.5 seconds, we're actually shortening the chord that we're dealing with, so it's just that long. And then when we go to 3 seconds, we're using the chord from here to here. And then when we go to 2.5 seconds, we're using this chord from here to here. And then 2.4 and 2.3, notice we're getting these really tiny chords. Okay? The idea is the closer we get to the exact time we want, the more accurate that average will be to the actual speed at that moment. Okay? Yeah.
Is this derivative the opposite of an integral?
Yes.
They are, basically.
So
Okay?
an integral would just be if you're taking the bigger of the you're expanding it.
Well-
The derivative you're making it smaller.
No. So we'll get to it. It's okay.
Yeah, my goal.
You're thinking. That's good. So, but let's start here. Let's start here with our function, with our point F, and find the slope. You and your partner, you can divide them in half and each do part of them. Okay? Find the slope from point F to these points down here. Okay? So you should get a different slope for each time. Each of those slopes will give us the average speed over that interval. Okay? So go ahead and try that.
What's that? Well, that's the instantaneous speed. You don't want that. You want the less accurate thing. So you're just gonna have to take the distance from it the same way we did this one, except you're using those t values and those. Yeah, except with the new values. So yeah, I mean, ideally you would have a calculator function for you, but how would we do that?
That's the one we got last time.
So this is what we're
You're doing the same thing we just did with the 0.4256, just with these points.
No, I'm not going to make a function. Try to do it
Oh yeah, that's it. Yeah.
So no, you're doing slope again with that point up there, 264. So you have to do y1 minus y2 over x1 minus x2. Or like distances subtracted over the times subtracted. Okay? Work together, guys. Okay?
So let's check my.
Just quit. I got it. I did it.
So what was the value that we got at 4? Before it was super. No, that's not right. It's
Oh, all of these you find the slope like between this point and 264. And then find the slope between this and 264. Because we want to find the speed at the point 264. So we want to keep using that as our reference point.
Okay, so
I wrote the equation just with this function right here, but I defined the x value as x and the y value as the entire as f. So this is the function basically, and we're going to take.
You want to use that as one of your points every time. So it's from here to here, what's the slope? And then from here to here, what's the slope?
Okay, so, oh, the function, okay, you want my function. Okay, so 16 times x squared minus 64 over x minus 2. And then you just graph trace for whatever x. This is just a specific for this problem. To solve it, but it's more. You know, it's the. This is right. I have no idea what it is.
So you're not doing the 264, so you're doing, or the 200.
Yeah.
It's the 0.2.
64.
That is 80.
Yes.
2.5. It's not it's slope.
We're just finding slopes here, guys.
And then 2.5 is
Shouldn't be terribly difficult.
It's 70.4.
Okay, what did you get for, let me see, what did you get for the first one? 88? Okay. And Alina, how about the second one? 80? Okay. What'd you get for this one? 2.5, 100.
Sorry, I did not. Remember last year you sang us the quadratic formula song?
Yeah.
You sang us.
Well, since we're not studying the quadratic formula right now.
Bottom up, so if you get to the lower numbers.
Okay. All right, I'll come back to you then.
We got 72.
72? All right, what'd you get for the next one? 70.4? Okay. Let's see, Biggie or Tony, what'd you guys get for the next one? 68.8? Okay.
13.
No.
And then, how about Hannah, or 67.2? Did you guys get the last one?
65.6.
65.6, okay.
Did you sing us a small song?
Not right now, okay? We have things we actually have to accomplish here. All right, so which of these is going to be the most accurate if we're looking for the instantaneous speed at 2 seconds? The one that has the average speed between 2 seconds and 2.1, okay? So you'll notice here, guys, what we're doing is we're narrowing that difference in the times to get closer and closer and closer to the time we actually want. Okay? Now, what we're doing here is we're really kind of developing the whole concept behind the derivative. Because the derivative is the slope, or rate of change, of the tangent line at a specific point on the function. Okay? Now, a lot of times what we'll do is we'll find the derivative in terms of x, and then we'll plug in specific x values to figure out what the slope is at that time. Okay? Please remember, a tangent line is one that just touches a curve. Okay? So here's an example. We have this tangent line. The point of tangency is that point that we're looking at, that we're focusing on, okay? And what we want to do is we want to evaluate the derivative at the point of tangency, and that'll tell us what the slope of the curve is at that point. All right? Because anytime you have a curve, it's curving because the slope is changing. Okay? But if we can get the slope of the tangent line, that tells us what the slope of the curve is at that exact moment. Okay? And that's going to tell us what the rate of change of the function is. In the case of our example here, if we're able to do that for this function, and then we plug in 2, that would tell us the exact speed at 2 seconds. In this case, it would be 64 exactly. Okay? because the derivative of this is actually 32t, and 32 times 2 is 64. So 64 feet per second is the instantaneous speed. All right, and as you can see, our approximation was getting closer and closer to that. So let's take this idea. We've been using the slope formula, and let's develop and derive this formula for a derivative, okay? The first thing that we're going to do is we're going to start with the slope formula. You don't need to, but I want you to understand. So I just want you to put everything down for a moment and just watch, okay? We're going to start with the slope formula and 2 points on the function. Now we're going to use these 2 points just as generic points. So one of the points is going to be x and f of x. The other point, and you'll notice we have this function here that we're dealing with. And we want to find the derivative or the rate of change at that moment right there, at this point x, f of x. So we add an unknown amount to x, and we call that difference delta x. All right? So it's x plus delta x for our x coordinate, and then of course we have to evaluate the function for that new value of x. All right? So basically all I'm doing is setting up the fact that we have 2 different points on the function, and notice that, remember how we were using the chord, finding the slope of the chord. Here, we're going to find the slope of this line through those 2 points. Okay? Now, if we keep in mind our slope formula, the slope formula is the change in our y values over the change in our x values. So, my y values are f of x plus delta x and f of x. So I'm going to subtract those in the numerator. And then my x coordinates are x plus delta x and x. So I subtract those. And notice my x's will cancel out, leaving me with a slope of f of x plus delta x minus f of x all over delta x. All right? Is everyone with me so far?
Just a function of like the original plus the change minus the original divided by the change.
Yeah. Good.
Isn't that just the slope anyways?
It is the slope. It is the slope. Now watch what we're going to do with this slope. What we want to do is, just like we saw with the times that we were dealing with, I want to take this point here, this green one, and I want to move it closer and closer and closer to the actual point I'm looking at. All right? And this is what this is going to look like, okay? We're going to move it closer and closer and closer. And what do you notice is happening here? What happens to delta x? It's getting smaller. In fact, it is approaching what? What? Well, we're going to, but what is delta x approaching? 0. It's approaching 0. It's getting smaller and smaller and smaller. And that right there, guys, is how we get the definition of the derivative. We look at it as delta x is approaching 0. And what we want to do, since we know delta x can't equal 0, because look, delta x is our, there we go, our denominator. It can't actually equal 0, but there's this asymptote there, and it's going to approach 0, and that means our whole slope is going to approach a specific value. Okay? So this gives us the definition of a derivative. Okay? And that's this. Here's that slope function we were just looking at, and the derivative is the limit of this as delta x approaches 0. Okay? Does everyone understand how this works here?
Like I understand the function,
Mm-hmm.
but I don't why we want it. Like you're just trying to get as close to, like when you drop the ball, you're trying to get as close to 2 as possible.
Mm-hmm.
Why couldn't you just get to 2?
Well, because if I try to find the slope at one point,
Okay.
then I'm dividing by 0. That's why we have to do the limit here, so we're not dividing by 0. Okay?
So what does it mean to take the derivative of something?
Well, it means to find the rate of change at a specific point. You have this function, and when you take the derivative of it, you're finding some kind of an expression or something that will tell you what the rate of change is. Because as that function curves, the rate of change is constantly changing as well. Okay? Now, we'll explain that a little bit more as we move forward, but I want to point out some notation to finish off here. There are 2 basic notations for the derivative. Okay? You have the derivative with respect to x. That's how you would read this, d over dx. The derivative with respect to x. And then also, you have the prime notation, f prime of x. And where these are most commonly used, you need to be familiar with both of them, but often when you're given a function written in terms of y, like y equals blah, 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 a lot of times they'll say find the derivative of y with respect to x, dy dx. Okay? Also, if the function was given as, in the function notation f of x, it'll often just say find f prime of x. Okay? So usually they're paired like that, but be prepared if you see the notation to recognize it either way. I'll emphasize this because this notation can be a little bit tricky to notice or pay attention to. All the formulas in your formula booklet are given in terms of this notation here. They don't use primes. So make sure you look over those formulas and pay close attention to what they're saying. A lot of the times, like with the chain rule or the product rule or the quotient rule we're going to learn it in terms of primes because they're just easier to write out that way. But make sure you could recognize what it's saying in the other notation as well. Okay? So, we will pick up from there tomorrow, looking at differentiation and actually doing some of these. Okay? All right, have a great day.